In this video, I'm going to answer problem 13 on page 8. Figure 7.1 and 7.2 show wavefronts of light approaching a plane mirror and a rectangular glass block, respectively. A. On figure 7.1 and 7.2, draw wavefronts to show what happens after the waves strike the surface. Because the surface is a mirror, the wavefront is going to reflect back to the median. To draw the directions of the wavefront, I'm going to use a protractor. First, draw a normal line at the intersection between the incident ray and the boundary. So the normal line is perpendicular to this barrier. Now align this hole with the intersection between the normal line and the surface of the mirror or barrier and place right here. Make sure the normal line aligns with 90 degrees, and this is your new zero. So now we are going to count to the left how many degrees up to this incident ray. So here we have 10, 20, 30, 40, 50, 60, 70 degrees. Now find the 70 degrees on the right. So now this is your new zero. 10, 20, 30, 40, 50, 60, 70. And mark where supposedly 70 is. Now remove the protractor and align the ruler with this dot and the intersection and draw an arrow about the same size as the incident ray. Measure the size of the wavelength of this wavefront. So the wavelength here is measured between those two parallel lines, which represent the crest of this wavefront. Like this. This is the crest, this is the crest, this is the crest, and so on. So all the crests, they are connected with this line. So we have another wavefront here. So this is the objective of these parallel lines that connect all the crests. So it's important to measure the distance between two crests because that gives us the size of the wavelength. So now that I measure, it doesn't matter if it's inches or centimeter, we just need a value to project on the other side. So this is what I have, and I'm going to move on the other side. I see here like 6 lines. Then on this reflected ray, you can place the ruler and mark the same size of those 6 lines to define where you are going to cut with the wavefronts. Now make sure that you have the wavefront perpendicular to the ray. So make a perfect L. So then you can start with the first one, and then the other ones just do parallel to the first one that you just did. This, and the last one. So here is the final drawing that shows what happened to this wavefront after it strike a surface, a reflective surface. Now in this picture, the wavefront is going to strike a glass block. So to draw the wavefronts after hit this transparent or semi-transparent surface, we need also to draw the normal line. At this time, the normal line will cross the boundary. We didn't do this here because the other side of the mirror is opaque. In this case, it's semi-transparent, so go straight. Now the light is going to travel between two mediums, air into glass. So because air is less dense than glass, so the light is going to bend toward the normal. So here is the line or the ray if we'll go straight. So then, because it's going to bend toward the normal, is going to this way. So here is a good location to draw the refracted ray. Now in this first picture, the light ray or the light wave did not change its speed. So here, speed is the same. For this reason, the length of the wave is conserved. So the same length that I have with the incident wave is equal to the same wavelength for the reflected wave. For the second picture, because the speed change, so the speed is decreased. So the wavelength is going to also decrease. The wavelength here, this distance at this side is gonna get smaller. So to draw that, we just need to get one line that is perpendicular to this ray, and the size should be less than those 6 lines that we have originally here. So let's say 1, 2, 3 maybe, and then we can keep going with this. So now I'm going to draw the wavefront. So as you see, the wavefront, even though it's coming with the same incident angle on both cases, this is also 70 degrees, is going to project differently depending on the type of surface it's going to strike. If it's a reflective surface, it's going to strike bouncing back with the same length of the wavelength. If the surface is transparent or semi-transparent like a glass block, it's going to pass through, but it's going to refract or bend, in this case, toward the normal. And the wavelength is going to be smaller than the original wavefront. So option A is completed. B, in figure 7.2, the waves approaching the block have a speed of 3 × 10⁸ meters per second. Okay, this is the speed of light in the vacuum. And an angle of incidence of 70 degrees. The refractive index of the glass block is 1.5. Calculate the speed of light wave in the block. This is Snell's law equation. We don't have velocity here, so this is not a good equation to use to calculate the speed of light in the block. Here is another equation for the waves unit. Is the speed of the wave is equal to the frequency times the wavelength. We don't have the frequency. We could measure the wavelength, but the problem didn't say that we can measure with a ruler and that will be the length of the wavelength. So we cannot use this equation either. The third equation, the third option, is the index of refraction is equal to the speed of light in the vacuum over the speed of light in the medium. So we have the index of refraction of the block, which is 1.5. We have the speed of light in the vacuum, and this is the speed of light in the block. So we can use this formula to calculate the speed of light in the block. So this is the original formula. After we arrange the formula in terms of the speed of light in the medium, in the case in the block, so we can calculate V, which is 3 times 10 to the 8 meters per second, over N is 1.5. So the easiest way to do it, so get this number divided by this number. So this is 3 divided by 1.5 is 2, and what is left here is 10 to the 8 meters per second. So the speed of the light was reduced as it's traveling in the block. The last part of the problem, calculate the angle of refraction in the block. So looking at the 3 equations options that we have, the only one that we can calculate an angle will be Snell's law. So let's use this one. N1 sine of theta 1 is equal N2 sine of theta 2. So N1 here is the air, which is the medium above the boundary line, and the glass is 2, which is the medium below the boundary line, the line between the divide both medians. So 1 here is air, which is 1 sine of the incident angle, which is 70. So sine of 70, and 2 is the glass block was given is 1.5 sine of theta 2. So divide both terms by 1.5. Now I have sine of theta 2 is equal to sine of 70 degrees. So theta 2 is, okay, so sine of 70 sine divided by 1.5 is this number, and I need to calculate the inverse of a sine of this. Inverse of a sine is 38.78. I can round to 39 degrees. So this is the angle of refraction for this situation here. So that is 39 degrees. Page 9, question 14. Figure 6.1 shows a rectangular block ABC, ABCD, and the ray FE is partially reflected and partially refracted at E. So I says, on figure 6.1, draw in the approximate path of the refracted ray within and beyond the block. Label the ray refracted ray. Okay, so first, this is the incident ray, which is at 60 degrees with the normal line. So the refracted ray will be toward the normal because the glass is more dense than air, so it's going to turn this way. So now you can draw a ray. It says within the block and now beyond the block when emerging the block. So at this point you are going to draw a normal line one more time, and now we have a transition between a medium that is more dense to less dense. So then the light is going to bend away from the normal exactly at 60 degrees. So you can place your ruler right here at 60 and slide a little bit and draw a ray that is going to represent the light emerging this block. So here is 60 degrees. So I is complete. I, on figure 6.1, draw the path of the reflected ray and label the ray reflected ray. Reflected ray is going to follow the law of reflection, which states that the incident and reflected angle are the same. So then place your protractor right here, and just to confirm, this angle is exactly 60 degrees. So here is 90, now is your new 0, 10, 20, 30, 40, 50, 60. Yes, at 60. Now remember, when you read a protractor, don't read these numbers, especially in this case that our reference is not 90, 0. So, and then it's important that you identify the angles, not following the marks, the number that you see printed on this protractor. Now on the other side, we have to find the also 60 degrees angle. So here is our new 0, 10, 20, 30, 40, 50, 60, right here. So you mark there, and now you are going to connect this ray that is going to reflect, make a little bit symmetrical, and that's the ray that is going to reflect off this block, and this angle here is 60 degrees. Now we need to label. This is the reflected ray, and this is the refracted ray. So then we complete II. Now I'm going to do B. A second ray almost parallel to AE, it strikes the block at E and is partially refracted at an angle of refraction of 43 degrees. State an approximate value for the angle of incident at E. So let me try to draw this. So what happened here is this incident ray is going to increase up to the point that is almost parallel to this line AE, like this. So this is the angle that makes with the normal. So it should be almost 90 degrees. And then, as a result, a light is going to appear in the block that is refracted at 43 degrees. So if this is 60, so it should be less. Let's make up to here. And this is what happened. So this is this angle right here with this one is 43 degrees. Because there's so many lines here, I'm going to just highlight this one, the green one, and I'm going to highlight the original one, which is 60 degrees, and we projected this way. That's the path. Oops. This is the path. Okay. Now the next question is, state an approximate value for the critical angle for the light in the glass block. So the next question is, state an approximate value for the critical angle for the light in the glass block. So in this case, the angle that we should be looking at is the one that is produced when the incident ray is almost on the surface, which is right here. So that should be the critical angle, 43 degrees. Now it's asking to calculate the approximate value for the refractive index of the glass of the block. So we are going to use Snell's law, and 1 sine of theta 1 is equal N2 sine of theta 2. We have 2 points here in this diagram. We have here and here. But what we have been looking at is what happened right here at this point. So the incident angle is almost 90 and the refracted angle is 43. We are going to use this information to calculate the index of refraction of this glass block, or N2. So the median above the line is the air, so N1 is 1, sine of 89, and N2 is the block, sine of 43. So now N2 is sine of 89 over sine of 43. So N2 is equal, grab a calculator, is 89 sine divided by 43 sine. So N is 1.46.